Hi, my name's Tyler Compton, and you're watching Gaming and Go. So in the last episode, we covered some basic graphics stuff. We got some sprites on the screen, created a white background, and all that good stuff. From here on out, we're going to start working on user input to get the user moving around. We're going to start drawing some enemies, and we're going to allow the player to shoot a bullet, and maybe some other stuff. We'll see where it takes us. So let's start off by talking about how we might move the player around. So let's take a look at what we have so far. So let me go ahead and build our project here. And okay, right where we left off, a white background with a player on it. So we want to be able to move this player left and right using the left and right arrow keys. And so the obvious next step here is to ask, well, how are we going to get keyboard input in SDL? Well, there's actually two ways to do it. The first way is to use the same event system that we used to have this quit event here. You know, where SDL collects a queue of events that happen over a period of time, and we take from that queue and handle these events one by one. That's a way that we definitely could do it, but it's not the way that I would personally recommend. For stuff like this, where we want to do something as long as we hold a key, I would recommend using a different way of getting user input, and that's using SDL's get keyboard state. So, okay, let's see how that would look. We're going to give player a new update function, and this, or method I should say. We're going to give the player an update method that is going to be run every frame and allows the player to do some operations that don't have to do with drawing that needs to be done every frame. So one of these is going to be to get keyboard input. So in order to use SDL.getKeyboardState, we just simply call it, and it returns a single item. So let's take a look at the documentation to give ourselves an idea of what we're working with here. So getKeyboardState returns an array of uint8s, or I should say a slice of uint8s. And so each element in this slice represents the state of a key on the keyboard. And we index this array using what SDL refers to as scan codes. So scan codes are just unique indexes for every keyboard key. So in this case, we want to know what the current state of the left arrow key is. So we might do something like if keys, and then we're going to give the scan code for left, which is just a constant inside of the SDL package. And then the value of these individual values is either 0 or 1. And 0 is the key is not pressed, and 1 means the key is pressed. So we want to check to see if this key is equal to 1. Okay, so inside of this if statement, we know that the left key is pressed. So if the left key is pressed, we want to move the player. So let's just go ahead and put something here just to say that that's what we're going to do. And, we want to check to see what the state of the right arrow key is. And so we just do the same thing for the right key scan code, and we're going to move the player right. But we don't really have a mechanism right now to keep track of the player location, and we don't use player location to figure out where we want to draw the player on the screen yet. So let's add that. In the player struct, let's add an x and a y value, and we're going to make those a float 64. And then inside of this draw, we're going to have to use this information in order to figure out where to put the player. Now, you might recall from the last video that we messed with, in the destination rect, its x and y value, and saw that that moved the player around. So that's exactly what we're going to do. We're just going to take the player.x and the player.y. And so this will change where this rect is that we're putting on screen that we're going to fill with the player sprite. But we got a bit of an error here, and all that the error is saying is that it doesn't expect a float 64, it expects an int32. And you're going to notice that anything in SDL that refers to some kind of coordinate or something like that is going to deal with integers. And this makes sense because SDL uses pixels as its unit of position. And so, there isn't really a space in between two pixels that a computer can draw to, so it would make sense that we just use ints. But for our sake, we want to keep track of our position as a float 64, and the reason for that is because it allows for more smooth movement. We want to deal with subpixels. A lot of other games do too. It's a very common thing, and it allows us to, for instance, accelerate player movement in a way that looks smooth, even if it doesn't necessarily map directly to individual pixels. But this cast to int32 just rounds it down anyway, so at some point we're rounding, but you're going to have to take my word for it for now. Having a float 64 is generally the way you want to go for keeping track of player locations, or any other location for that matter. So, okay, great, we're doing that, and if we recompile the program, we can see that No surprise, the player is at 0, 0 now because that's the default value for x and y. But that's probably not what we want. But before we get too into that, let's try and move the player around. So when the player is pressing the left button, we want to subtract from the player's x value, right? Because if you recall, SDL's coordinate system is such that 0, 0 is on the top left, and x as it increases moves to the right, and y as it increases moves down. So we're going to want to subtract from the x here by some amount. So let's create a constant for ourselves here that represents the player's speed. And it's not really super clear immediately what the player's speed should be, so let's do a bit of experimentation. Let's start at 1. So x minus equals the player's speed, and so now every frame, as long as the player is holding down the left button, the player will move player speed units in the negative x direction. And then when we're moving right, we want to do just the opposite and move in the positive x direction by player speed units. Okay. All right, so let's see, we're getting an error here. Oh, and it's just because it's not x, it's player.x. It's the player's x value that we're editing. Okay, so let's take a look here. All right, so, and it doesn't work, and I can tell you exactly why. It's because we need to make sure that we actually call this update function or method, and we want to do this inside of the main loop every frame, just like we call the draw frame, or the draw method every frame. So if we do player.update, okay, now update is run every frame. So let's take another look here. Okay, and there you go. Well, we're moving the player, but it's a little too fast. So let's go ahead and revisit that speed. And let's try something way slower, like 0.01. It's 100 times slower. And okay, that might be a little bit slow. Let's try 0.05. And okay, I think that's pretty good. But if you played a shoot 'em up before, you know that the player doesn't usually hang out at the top of the screen, they hang out at the bottom. It's usually enemies who are at the top, and that's why they call it a shoot 'em up, right? You shoot up towards the enemies. So let's set that player default position to be something a little more reasonable. I think that the reasonable position would be in the bottom center of the screen. So we just want to set the player's x to be the screen width divided by 2, and the player's y to be the screen height. And right now, the x and y values refer to the top left of the sprite, so we're going to have to do screen height minus the size of the player's sprite. Let's create another constant to represent the size of the player's sprite. So I happen to remember that the player's sprite is both in the width and height 105 in size. So we're just going to have a single value that is equal to 105 that we're going to use. And okay, there we go. So let's take a look at that. So, okay, it's a bit weird because we're just a little bit off center. And it's again because we're representing these points in the top left of the sprite. And personally, I don't think that's very intuitive. I think instead we should have the x and y values of the player represent the center of the sprite. So we can just do that. We can just say, okay, now they represent the center of the sprite, but SDL still expects them to be the top left. So every time we draw, we're going to have to do a bit of an operation here just to transform these x values to represent their top left. So to do that, it's just a simple matter of doing p.x, the player's x value, and subtracting it by half of the player's size. And the y value, we're just going to do exactly the same thing. And so instead of making use of the player's x value, we're going to use this transformed x value. And let's just add a comment up here because it's a little bit of weird logic here. We're converting player coordinates to top left of sprite. Okay, perfect. So, okay, now he's at the center, but that transformation we did to make sure that he's not being cut off at the bottom isn't really necessary, or I should say, it's going to look a bit different now. We want to do player size divided by 2.0 because after all, now if we just didn't do that, it would cut off half of the player instead of the entire player. So we want to move that half up such that the player is now fully visible on screen, completely centered, and now this looks quite a bit more like a shoot 'em up. But what are we missing here? Well, I would say the first thing, the most obvious thing, would be enemies. So let's talk about how we might put enemies on screen. And really, it's going to be almost exactly the same as how we put the player on screen. So if you recall, we've got this player_enemy.bmp file here, and this is just a, not super good sprite representing a basic enemy that we can draw on screen. So let's go ahead and use the same pattern we did for the player and create a brand new type called basic enemy in a new file called basic_enemy.go and go from there. Okay, and we're going to need an STL texture, of course, because we want to be able to render this guy on screen. And we're probably going to want X and Y coordinates representing the position of this enemy. So in fact, let's go ahead and put the player on the side here just as reference, because we're probably going to be doing a lot of the same stuff. So let's create a new function here that creates a new basic enemy, and it's of course going to need a renderer because it's going to be doing some rendering operations. And so I suggest that we take the X and Y values in as arguments as well, because unlike the player, there isn't really an obvious location where an enemy should go, some kind of obvious default. We probably want to set that as we create the enemy. So let's go ahead and take those as arguments. And we're going to return a basic enemy and an error if we encounter any errors. Okay, so we're going to be doing basically the same thing here. Just load the image from the sprites directory. In this case, the sprite is called basic_enemy.bmp. We're going to want to replace these error descriptions to show that we're talking about basic enemies instead of the player. Okay, and instead of returning players, we want to return basic enemies. Okay, and then we just want to return our result here. And all right, we're off to the races. So we've created a new basic enemy, but it's not very useful to us until we have at least a draw method so we can see that we've created one in the first place. So let's add a draw method, and this is also going to look very similar to how the player drawing looks. And in fact, it looks so similar that I accidentally made it a method of the player instead. Let me fix that. And it is going to take a renderer because we're doing rendering operations after all. And we're going to have to convert the player coordinates, in this case basic enemy coordinates, to be the top left and do a renderer.copy. So almost exactly the same thing. And so in order to convert our coordinates to represent the center of the enemy, we need to know the size of the enemy sprite. I happen to know that it's actually the same as the player size, but let's create a new constant anyway to just make it clear what we're referencing here. It might be a bit confusing if we recycle the player size value. So we're going to make a constant called basic enemy size and have it equal 105. Okay, and we're just going to replace, we're going to replace these here. Go ahead and reference a basic enemy instead of the player, and draw the basic enemies texture instead of the player texture. And okay, we've got a very basic drawing method, just like the player, in order to draw the basic enemy. So, okay, I think that we're ready to make use of this new object, or this new type. So let's just create a new one just right here, right in the main method or function, just in the same place as we create a new player just for testing. And we're going to call it enemy. And let's see, what place should we put it to start off? Let's put it at the center of the screen, just because it, it seems like as good a place as any. Okay. And of course, if we encounter any errors while creating this basic enemy, we want to let ourselves know. Okay, and perfect. So let's go ahead and draw this enemy right after we draw the player. And okay, let's see what we've got. Okay, I must have made some kind of mistake here setting the position. Oh yeah, look at that. I forgot to set the actual basic enemy's position that we get as an argument. So let's go ahead and fill that in. Okay. All right, now we're talking. So now we've got an enemy drawing on screen in the very center, but you might notice a bit of a problem here. Generally speaking, if you played like Galaga or Space Invaders before, usually the enemies face the player, and that makes the most sense, right? So we're going to have to rotate this sprite in some way. But how are we going to do that? If we look at renderer.copy, which is historically where we've done a lot of transformation operations, we can see that we can change the width and height and change the position, but I don't see any way of doing a rotation using this method. Well, there isn't a way with this method. However, we have a new method that we can work with called copyEx. So let's look in the documentation to see what that is. So copyEx is basically a superset of the copy method. It takes the texture that we want to draw, a source and destination rect, just like copy, but it also takes an angle, which you might immediately think is important, a center point, and some kind of flip value. So the angle is exactly what it sounds like. It's the angle with which we can rotate the sprite, and this is what we're mainly interested in here with copyEx. It also takes a center point though, and a center point is just the point with which the sprite is being rotated around. People who have done graphics programming and stuff like that before will probably be immediately familiar with why this is important. The important thing for us right now is that we want the center point to be the center of the sprite itself. We want to pivot along the sprite's center. And chances are, if you were thinking about rotating the sprite, that's exactly the kind of behavior that you were expecting. This flip value we're not going to use. It just allows us to mirror the sprite either horizontally or vertically. We don't need that right now. So we're going to pass a none value to that. We'll see that later. So let's go ahead and instead of renderer.copy, let's do renderer.copyEx. I want to mention that this is a pattern that you'll see often in SDL is there is a method or a function with some name that has a few arguments, to tailor to the most common use case, and then they have an EX version of the method, which often has more arguments that you might need in slightly more advanced scenarios. So, okay, the next argument for copyEx is the angle. So the angle we want to rotate this 180 degrees to make it face the opposite direction that it's currently facing. So we're just going to give it 180. The center point that we want to rotate on is the center of the sprite itself. And we hold the center value in our X and Y of the basic enemy, but that's not the center value that it wants. This center value is not relative to the entire world space. It's actually relative to the coordinate system of the sprite itself. And that might sound a little bit weird, but it's not too awful complicated. Let's open up the basic enemy bitmap here in GIMP so I can kind of illustrate what I'm talking about here. So this you could say that the sprite has its own coordinate system where the top left of the image is 0, 0, and the bottom right of the image is, in this case, 105 by 105 because that's the size of the image itself. We want the pivot point to be in the center. So in this case, it would be 52.5 by 52.5 would be the value that we'd want to give copyEx. So let's do that. We're not going to hard code in 52.5 by 52.5 though. We're going to go ahead and do basic enemy size divided by 2. But of course, this is inside of an SDL point. So we're going to create an SDL point in the same way that we create a rect, just using a struct literal that with the ampersand pointer syntax. And basic enemy size divided by 2 again. Now we've created a center point that is at the center of our sprite. The last thing that we need to give it is a renderer flip value. So the renderer flip arguments take some small set of constants that represent either a vertical, horizontal, or like no flip. So let's take a look and see if we can find these. Flip. Okay, here we go. So we have flip none, flip horizontal, and flip vertical. We're not interested in flipping, so we're just going to use SDL.flipNone. Okay, perfect. So let's just do a quick review of what we did here. We gave copyEx the texture that we want to draw, a rect which decides what area of the sprite itself needs to be drawn, which in this case we're saying the entire sprite, a destination rect which references where in the screen itself we want to draw the sprite, which in this case is the X and Y values of where the enemy is and the width and height of the sprite itself. The third value that fourth value that we give it is an angle in degrees. So it's 180 degrees to flip the entire sprite around. A center point with which to rotate the sprite, which is in the center of the sprite. and a flip value to say if we want to flip it or not. And we don't want to flip it, so we just gave it flip none. Okay, so let's take a look here and see if it all worked. All right, perfect. So now the enemy is facing the player. That's great. But again, I don't know how many shoot 'em up games you've played that have just one enemy in them. In fact, they usually have a grid of enemies, don't they? Maybe like, you know, a 5x3 grid of enemies across the top of the screen that you have to defeat in order to get to the next level. So let's go ahead and implement that. So in main.go, right now we have just one enemy. But let's not do that. Let's have a slice of enemies. And we're going to populate these slice using 2 loops. So in this case, I'm going to say that we want to create a grid of enemies 5 across and 3 down. So that would be in total 15 enemies that we're creating. So we're just going to create 2 for loops inside of each other, with one representing, I is equal to 0, I is less than 5, I plus plus, and create another loop inside of it that represents sort of the y direction of the grid. Okay, so in here is where we want to create the enemies. So we're going to use this loop information to decide what the position of the basic enemies will be. So, okay, in the x direction, or I should say the x coordinate element, we're going to want to space these enemies across evenly. And in order to do that, we're going to write some code a bit like this. So let's go ahead and do I. We're going to have to turn I into a float and divide it by 5. So this is going to create a value between 0 and 1 that will represent where on the screen we want to draw this enemy. And we're going to multiply it by screen width. Okay, so now we've created a portion of the screen width that this enemy should be drawn in order to be spaced evenly. So as for the Y position, we're going to do something fairly similar. We want to space these evenly once again, but in a top section of it. We don't want to span the entire height of the screen because then we'd have enemies all over the place. We want to span a small collected area. So let's say that we want to space the enemies as compactly as we can without their sprites overlapping each other. So what would that look like? Well, it would probably look something like just j times the basic enemy size. And I think that that should be it. Yes, I believe that's all we need. So, okay, now that we've figured out the x and y position that we want to place the basic enemy, let's go ahead and create a new one. I'm going to give it a renderer, a x value, and a y value. I'm going to check that error to make sure that nothing bad happened while we were trying to create a new enemy. And if it does, we're just going to print about it. Okay, let's see, where did I mess up here? Oh, right. So because j is an integer and basic enemy size is a constant, you know, the constant takes on the type of the most, I'm not sure what the word is for it, the most capable, I suppose, number value. So we're going to have to convert this to a float 64 so that y turns out to be a float. Okay, perfect. So let's see what we get just by doing this. Well, actually, let's not. We're going to have to draw these enemies. So let's go ahead, after I fix this typo here, enemies declared and not used. Oh, right. So we created this enemy. We need to append it to the enemies list. Okay, perfect. And we can get rid of this test enemy that we created here. Okay, so now we need to make sure that we draw these enemies every frame. And we're just going to do that by ranging over all enemies and drawing each one. And of course, we need to draw a renderer. Okay, let's see what we get just from this. Nothing. Interesting. That's not what I was expecting. Okay, let's see. What did I do wrong here? Oh, okay, I see what I did wrong. This is an extremely rookie mistake, but hey, happens to all of us, I guess. We need to start j off as 0. Okay, and we can probably get rid of the slog because I feel fairly confident that that was the problem. Let's take a look. Okay, now we're talking. So, okay, the position isn't quite right because we need to remember that the position of an enemy is defined as the center of its sprite. So we're going to have to do a bit of offsetting here to say that we want to offset every enemy by half of the enemy's size, because as you can see, half of the first few enemies we were drawing are being cut off in the X direction, and all of the top ones are being cut off in the Y direction. We need to add an offset of basic enemy size divided by 2.0 for both of these. Let's go ahead and do that. And all right, perfect. That looks pretty good. So now we've got this, I would say, rather imposing group of enemies here at 5 by 3. So we've created 15 enemies. And you know what? These enemies are just begging to get defeated, right? Let's start adding that bullet functionality. So in order to add a bullet, we probably want to create another type, right? Probably the type would be called bullet, and it would contain information on how to draw the bullet and, you know, the position information and things like that. But there's a lot of things to consider about a bullet that we haven't had to consider about other objects, because historically we've been creating these objects before starting the program. We just created them in one fell swoop, but in this case bullets need to be created on demand depending on when the player shoots. So it's a bit of a tough problem, because right now when we create a new object, we go to the file system and load up a sprite, but we don't really want to do that every time the player shoots. So some of you may see this as a bit of a finite resource issue, and a lot of times finite resource issues are solved with pools, and that's what I'm going to propose. I propose that we keep a pool of bullets, not all of which are active at once, but it's a pool that we can pull from anytime a player or maybe an enemy or something else wants to shoot a bullet. So, okay, before we get too ahead of ourselves though, let's just start creating that bullet class, or bullet struct, I should say. So of course the struct is going to contain a texture because we want to be able to render it on screen, and it's going to contain a position on screen. And all right, so we're going to be writing a lot of code that probably looks very familiar to you at this point, because we've done it both for the basic enemy and for the player. So let's create a new bullet function, which of course creates a new bullet. I'm going to give it a renderer, and I'm going to say we don't give it an X and Y value right now, and you're going to see why later. All right, so for this, we're going to return a bullet. We're just going to call it bool as shorthand, and an error if, an error occurs. Okay, so I'm about to write this, load BMP, create texture from surface thing all over again. And I'm starting to think that after the third time we wrote it, it's probably time to create a new function for it. So let's go ahead and make a new function in main.go, and let's call it texture from BMP. And texture from BMP is going to take a renderer and a file name. And this file name will of course be the BMP file that we're going to load and turn into a texture. And we're going to return just an SDL texture. And I'll tell you why. I don't think we should return an error here. And the reason why I say that is because almost every time this error is if an error happens in texture from BMP, it's going to be because the programmer got a name wrong in the sprites, which in this case would be me. And I wouldn't put it past myself. But that is a programmer error. And it's also an error that if it happens, we don't really have a way of progressing. We need to load all of these sprites in order to be able to play the game. So I think that we should panic here. And that's not generally something that you want to do in Go. You generally want to return an error in most circumstances. But in this case, because there's really no way to progress if this function fails, I don't think it's worth having errors all over the place, specifically for this kind of failure. So I think we're going to panic. But other than that, it's going to look very similar to this code that we've already written a couple times. Instead of, loading a basic enemy, we're going to load from the given file name. Instead of returning an error, we're going to instead, I'm going to close this window here just to give us a bit more space. We're going to instead panic, but we are going to be good gophers and provide a little bit more context here. Loading, and we're going to give the file name that we're loading and the error that occurred, but we're going to panic there. Instead of setting a basic enemy's texture here, we're just going to create a new variable called text, which we're going to later return. And if an error happens here, we're going to do something very similar where we're just going to panic. And I'm going to say creating texture from, and then I'm going to give it a file name. So if we get an error, it should be relatively easy to track down where it happened. Okay, and then we're going to go ahead and return the texture that we created. So before we use this in bullet, let's go ahead and utilize this in basic enemy. It's going to become quite a bit simpler all of a sudden. We just have to do this and give it a sprite location. Okay, perfect. And do the same thing again in player.go, in new player. Okay. And all right. And then we just do that once again inside of bullet. So this is going to be a player bullet. We're going to assume for now that only the player is shooting bullets. That may not be the case in the future, but for now that's what we're going to stick with. Okay, and we want to go ahead and return the bullet we created. But you might notice that we're returning all these errors inside of these new player, new basic enemy functions, and we don't have an error condition anymore. So let's go ahead and get rid of those. Okay, and the bullet itself will not need to return an error anymore either. Okay, well that's a pretty simple new bullet function, isn't it? All right, so let's go ahead and create a draw method because we know we're going to need it. And this is going to simply do the same thing that most other draw methods do, convert the coordinates to center coordinates, and then use renderer.copy. We don't need any special copy EX functionality here. We don't need to rotate the bullet at this time. However, what we do need is the bullet size. I happen to know that the size of the bullet sprite is 32. So let's go ahead and use that. And instead of referencing players everywhere, we're going to reference bullets instead. Okay, perfect. So, all right, about that bullet pool, let's go ahead and implement that. And I'm going to go ahead and go out on a limb here and make the bullet pool a global variable. I know, usually we wouldn't want to do that. But game design, at least in my experience, is a little bit different from other fields in that global variables are actually quite a bit more common, at least in my experience. And the reason for that is because games are not often parallelized. That is starting to change now, but especially for simpler games like ours, there isn't that many concurrency or parallelization opportunities available because a lot of times every event is strictly dependent on other events. And so historically, we found that games don't utilize CPU that hard anyway. It's more of a GPU operation. So I'm just going to go ahead and create a global variable. Do with that what you will. But I think it's going to work out well for us. So we're going to go ahead and create a bullet pool, which is just simply going to be an array of bullets. So let's create a function called init bullet pool. And this is going to fill the bullet pool up with bullets. And so I'm not entirely sure on how many bullets we're going to need, so let's just use a number that's probably higher than we need because bullets are not that expensive. Let's make 30 bullets inside of the pool. So we're just going to go ahead and we can probably just do bullet pool equals append. Just go ahead and append to this bullet pool slice and create a new bullet. given a renderer. So we're going to need to give init bullet pool a renderer as an argument as well. Okay, perfect. All right, and now we're going to create a convenience function that searches in the pool for an unused bullet and returns it. So bullet from pool. And so any entity that wants to shoot a bullet is going to use this bullet from pool to get a bullet and then do whatever operations it needs to do on it. So we're going to return a bullet and a Boolean. And this Boolean may actually be a pattern that is familiar to you if you've used Go for any period of time. It's often referred to as the comma OK pattern. And it's a pattern used by Go both internally and by libraries and the like, which is used for operations that may or may not succeed, but the failure condition isn't really an error. So for instance, accessing a map value that may or may not exist in the map, you can use a comma OK syntax like this, where it returns the value in the map if it exists and an OK value. You can check this OK value to see if it was a successful lookup in the map, as in if it was actually in the map or not. We're going to be using it in this case to represent a situation where the pool is exhausted and there are no bullets available. We're going to return false in this OK value if that's the case. So we're going to loop through the bullet pool and try to find a bullet that is not currently being used. Okay, so now we run into a bit of an issue. How do we know if a bullet is used or not? Well, bullets are kind of interesting because we create them without actually wanting them to be shown on screen or be, an active member of the, larger gaming space until we want to use it from taking it out of the pool. So I'm going to give bullets an active Boolean. And when this is true, it means that the bullet is in use. And when it's false, of course, that means it's not in use anymore. So I'm going to make it such that if the bullet is not active, it's not going to be drawn. And you can imagine in future operations, we give the bullet, if it's not active, the bullet should be ignored. So now we can go over here and check to see if the bullet is not active. And if it's not active, we can assume that it's unused and we can return it to the caller and say true to say that we're okay. We were able to get a bullet from the pool. However, if that never happens, we can go ahead and return just some empty bullet object and false to say, no, we did not get a bullet from the pool. The pool was assumedly exhausted. Okay, one thing I'm going to say though is that you'll often see in pools like this, more often than not, they hold pointers. And the reason for that is because if a caller of bullet from pool wants to change the bullet's active state, well, they're going to be changing a copy in this case, because when this bullet is returned, it's returned by value, meaning that it copies the bullet itself, and the changes will not be reflected in the bullet pool. So instead of holding these bullet values, let's hold pointers instead. And that's not going to change too much of how we use it, but we're going to have to take this new bullet call out here and append a pointer to this newly created bullet like so. And then we're going to, of course, have to change this syntax a bit to show that bullet from pool returns a pointer. And now, if we can't get a bullet from the pool, we can just return nil. Okay, perfect. So now we've initialized, or I should say we created a bullet pool. And we can use this anywhere where we want to shoot a bullet. So where would we want to shoot a bullet? Well, probably in player, right? So let's take a look here. And we want to listen for the space key. That's going to be our shoot key. So if we do keys, SDL.scan code, and there's a scan code for the space bar that's just called scan code space equals 1, then the space bar is pressed and we want to shoot. So in order to do that, we're going to get a bullet from the pool. So if bull OK, and we're going to call bullet from pool. Okay, so this means we get a bullet from the pool and check to see if we were successful in getting one from the pool. And if we are, then we're going to set that bullet to be active. And we're going to need to set the bullet's position. For now, let's just set it to the position of the player. Okay, perfect. All right. And of course, we're going to need to call this init bullet pool function somewhere. Let's just call it near the very beginning of the main.go and give it a renderer. And you can see we've got some errors here. And if you recall, this is because we don't return errors on these new player, new basic enemy functions anymore. So let's go ahead and just get rid of those. We're really reducing the amount of code that we have to write significantly by not handling errors. Not something I'd usually recommend, but in this case, for the reasons that I talked about earlier, I really do think it's the right call here. Okay, let's just go ahead and clean that up and run it. And okay, so what happens if we press space? Well, nothing. And the reason why is because we're not drawing the bullets yet. So we just need to go in here and loop through the bullet pool and draw each one. Now remember, it's the job of the bullet to decide if it should be drawn or not based on its active value, so this is all we need to call. So if we go ahead and build this, well, it still doesn't work. That's a bit odd. Okay, well, let's do a bit of debugging here. So let's just make sure that this is getting called in the first place. Well, it's not. Interesting. Why would that be? So maybe the bullet pool is just exhausted right off the bat for some reason. That would definitely indicate a bug, but let's see if that's the problem. Yes, it is. And you also notice that we're calling this a lot. And just as a reminder, this is because this update function gets run every frame. And for this kind of simple program on a modern computer, we get a really high FPS. And as a result, this scan code space check here happens quite a bit every second. So that's going to be an issue that we're going to have to figure out. But it looks like the bullet pool gets exhausted right off the bat, which is a bit odd because we really are appending to this bullet pool here. And new bullets have an active value of false by default. So I'm not entirely sure what's going on here. Oh. Okay, I figured out the problem. Apparently, I'm just not very good at writing for loops on camera, but let's just go ahead and change this to less. So we're looping from 0 to 30 instead of looping from 0, checking if it's 30, and immediately exiting the loop. Okay. All right. Well, okay. So it looks like there's a bit of an issue with rendering the bullet, but in general, the bullet was created, which is good. Unfortunately, a lot of bullets were created, probably 30 bullets if I had to guess, for the same reason that we were talking about earlier, where pressing the spacebar registers quite a few bullet shots just because of how quickly our game is being rendered at. So that's going to be an issue that we're going to need to address, but first let's figure out that weird bullet rendering issue. Oh, and that's because we're using 105 here. Okay, well that's indicative of two problems. First of all, we're of course going to have to change this to the size of the bullet instead of the size of probably the player, is where we got this from. And we're also going to have to change those 105s to a constant just for the sake of good code practice. So let's go ahead and do that. So where was that at that we copied and pasted this from? Yep, it's from player. Okay, so let's go ahead and fix that. Player size, because we don't want to have magic numbers in our program. That's something that we want to avoid if possible. Okay, and then if we go to the basic enemy, we can see that, well, I made the same mistake. It just didn't bite me this time because enemies happen to be the same size as the player. So let's go ahead and fix that as well. Okay, now I have a feeling that all is going to go well. And hey, there we go. We're rendering a bullet correctly. But we're rendering quite a few bullets correctly, so we're going to have to fix that. And probably the way that most games do that is by having some kind of shooting cooldown. You're not allowed to, in most games, to shoot as quickly as possible. You're probably allowed to shoot only, say, 4 times per second or something like that. So let's implement that. And we're going to be doing that using the time standard library package by keeping track of when the last time was that we shot a bullet. So let's go ahead and do last shot here as a player attribute, and it's going to be of type time.time. Okay, so then every time we shoot, we're going to want to update last shot to be the current time, or time.now. And p.lastShot equals time.now. Okay, so let's go ahead and get rid of these logs here, or at least this log here, because we already have it working. And so, okay, we only want to shoot if a certain period of time has passed since the last time that we shot a bullet. So what is that period of time? Let's define it as a constant. We're going to call it player shot cooldown. And let's make it such that the cooldown is every quarter second, so that you can shoot 4 bullets every second. So we're going to do that by doing time.millisecond times 250, because there's 1,000 milliseconds in every second. So if we go ahead and check here to do if time.sense p.lastShot is greater than or equal to the player shot cooldown, then that's when we want to shoot a bullet. Okay, perfect. Let's see if this worked. Okay, so now we're not shooting bullets and warp speed, we're shooting them at a much more reasonable speed. But it looks like we're placing potatoes on the ground right now because they're not going in any direction. So we're going to want to fix that. Let's go ahead and add that functionality. So a bullet has some kind of speed that it goes at in the sky, but it also has some kind of angle with which it decides which direction it's going to go. So that's going to be something that we're going to want to set. So let's go ahead and have every bullet have an angle attribute. And this angle attribute is going to inform us how we're going to want to move the bullet. We're also going to want some kind of bullet speed. So let's make that a constant. So bullet speed is equal to, well, okay, so the player's movement is 0.05, so we probably want it to be substantially faster than the player, so let's say 0.2 for now. Let's see where that takes us. Okay, and so we're going to want to move the bullet a certain amount every frame, and that sounds to me like a job for an update method. So let's go ahead and create a new update method for the bullet. This is something that we're going to want to call every frame. So we're going to go ahead and update the bullet's X and Y positions by some amount. And this is going to be a bit of trigonometry here, but it's not very complicated trigonometry, I promise. We're going to do bullet speed. So that's the speed that the bullet needs to move in the direction that it's going. And we're going to multiply it by math.cosine bullet.angle. And we're going to do something similar with the bullet's Y movement. And we're going to do bullet speed, or not bullet size, bullet speed times math.sine bullet.angle. So, okay, if this isn't something that you're immediately familiar with, then it's completely understandable. But the cosine and sine operations basically create a value between 0 and 1 that decides how much of the bullet speed should go in the X and Y directions. So in the case of if we were to move the bullet straight down, so without any X movement, cosine of that angle, which would be probably 270, would be 0. So it wouldn't move at all in the X direction, and sine of that angle would be 1. Meaning that all of the bullet speed is concentrated in the Y direction. So it's not super important to have a really innate mathematical understanding of what's going on here, but that's the gist of it. So, okay. So now that we've added this angle value, that's another thing that the player object needs to set when we're shooting a bullet. So bullet.angle, and I think it's 270 degrees, but cosine and sine expect radians, not degrees. So let's go ahead and convert that. And this is just the function for converting degrees to radians. It's just pi over 180 times the degrees. And okay, so now we just have to make sure that we call that update every frame. So bool.update. And then let's take a look and see what happens. Okay, perfect. I'm kind of surprised I got that 270 degree thing right. The bullets, I think, are just a little fast, but in general, I think it looks really good. So let's do 1.5. Okay, I think that's perfect. So there is a bit of a problem here though. We're only shooting one bullet, but the spaceship has 2 turrets on it. So let's fix that. So first thing that I want to do is this bullet shooting behavior is kind of becoming a bit complicated, and I think it might be a good idea to pull that out into its own method called shoot. And this will just have the player shoot a bullet. And this is going to be a method that we call twice every time the user presses space because we want to shoot 2 bullets. So as a result, we want all of this behavior in there, but we don't want to worry about the cooldown behavior in this area because we don't want to have a cooldown between the 2 bullets being shot. We want to shoot 2 bullets and then have a cooldown. So that's what we're going to do. So we're going to move all of this cooldown behavior over here. We can probably get rid of this log because we know that this stuff works. And then we're just going to do a simple p.shoot, and we're just going to do it twice. So let's see what that looks like. Okay, well, you know, we probably are shooting 2 bullets, but you wouldn't know it because they're getting shot in the same place, and so they're just on top of each other. So we want to create a bullet at some offset such that it looks like it's coming out of each of the spaceship's turrets. So in order to figure out that offset, let's go into an editor here. So let's edit player.bmp in GIMP just to get an idea of, just a rough idea of what the offset from the center to each of the turrets is. So it looks like it's around 25 by 20 from the center. So let's use that. So let's give this shoot method an x and y value, which decide where this bullet is going to be created at. So instead of creating it, just putting it at the center of the player, we're going to be putting it at these values. And for each shot command, we're going to do p.x plus 25 and p.y plus 20, and then p.x minus 25 and p.y plus 20. So there are slightly different offsets each time to shoot on the right turret and the left turret. So let's see if this works. Oops. Oh, right. Okay, so I made a bit of a mistake here. And this is very easy to make with SDL's coordinate system. But if you look really closely, you can see that the bullet seems to be coming from the bottom of the ship instead of up near the top. And that's because I added to the y value, which moves things down because y, as it increases, moves down in SDL's coordinate system. So let's just go ahead and fix that. Okay, that's great. I think that looks really good. You might also notice, though, that not to anyone's particular surprise, we've run out of bullets in the bullet registry because, well, we probably created 30 bullets at this point. But that's not really what we want. We want these bullets to get thrown away so that they can be reused once they're off screen. I mean, they don't really mean anything if they're off screen. So let's just go ahead and add that functionality real quick. So it's pretty simple. Let's just have the bullet be in charge of that. After it moves, let's go ahead and check to see if the bullet's x value is greater than the screen width, meaning that it's off screen, or the bullet's x value is less than 0, meaning it's off screen in the left direction. And let me just spell bull correctly. And we'll check to see if the bullet's y direction is greater than screen height, meaning it exited out the bottom of the screen. And of course, check to see if the bullet's y is less than 0, meaning that it exited off the top of the screen. So if any of these things are true, the bullet is off screen and we don't care about it anymore. So let's set that active value to false. All right, so now we should find that the bullets, we can just shoot them all day long. They get destroyed when they reach the end of the screen, and so we just have effectively an infinite amount of bullets at our disposal, considering we can only shoot them so fast. Okay, so there's one last thing I want to do before we wrap up this video. So you might notice if we go ahead and run the program here that the player can just kind of go right off screen, and that's not really ideal. We probably don't want that. So let's go ahead and just add a constraint here to the player movement to make it so that that's not possible, in a way very similar to how we did it with the bullet. So if we just go ahead and when the player is trying to move left, we want them to move left unless they're about to exit from the left side of the screen. So we want to say if p.x is greater than 0, then that's when we're going to allow the player to move left. Though, remember, these x and y values represent the center of the player, so what we really want is if p.x, what would it be? It would be p.x minus the player size divided by 2. So to make sure that the player's left side is not already out of frame, then we'll allow them to move left. Otherwise, we will not. And then for moving right, we're going to do something very similar. So we're going to say if p.x is less than screen width, then we'll allow them to move to the right. But of course, we do need to adjust this a bit because, again, the coordinates represent the center of the player. So you want to say if p.x plus player size divided by 2.0. All right, and let's go ahead and give that a shot. Okay, and perfect. The player is not able to exit the outside bounds of the game anymore. So we did a lot in this episode, didn't we? We got the player moving and not moving outside of the screen. We got bullets being shot. We got some enemies on screen. And now it's starting to actually become something that you might call a game. Of course, the next step would be to maybe, have the bullets actually hurt the enemies, have the enemies provide some threat to the player and stuff like that. But that's not actually what we're going to cover in the next episode. We will cover that eventually, but just not immediately. The next thing that we're going to cover is a bit of a structural, code structure related thing. We're going to take a look at the way Unity handles interactions between different game elements and how game elements are defined and things like that, and see if there's anything we can learn from that and if we can implement it in a reasonable way in Go. So until then, I'm Tyler Compton, and thanks for watching.